Mas Zaki, I think it's time.
Yeah, I think we can start, Mas Zaki. Mungkin nanti saya bacakan atau Mas Zaki ini ada ininya apa CV-nya Dr. Reddy.
Oh, sebentar. Sebentar, Pak. Ya, sebentar. Mungkin.
Ada nggak? Kalau nggak ada nih ada sedikit uraian.
Halo, suaranya back sound semua, Pak. Sebentar saya cek.
Iya.
Suaranya back sound semua, ada yang saya matikan dulu sebentar.
Baik. Saya barusan kirim WA ke Pak Zaki, itu mungkin bisa dibacakan untuk CV singkatnya Dr. Reddy ya.
Ya, baik, Prof.
Nah, mungkin nggak usah semua, tapi yang paling pertama di depan sana itu kayaknya informasi yang lebih utamanya di sana. Walaupun di bawahnya banyak sekali listnya itu. Silakan Pak Zaki.
Iya. Oke, sebentar. Saya matikan dulu sound-sound yang back sound dulu.
Oh, gitu ya?
Iya, banyak yang back sound sebentar. Oke.
Iya.
Oke, saya buka ya, Pak.
Silakan Pak Zaki.
Oke, good morning. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much for coming today, Dr. Reddy. And today we will have a guest lecture from Dr. Reddy, and I will try to read a brief CV about Dr. Reddy. Dr. Reddy is currently working as a senior researcher in Institute of Research Hydro-Quebec at the Center of Excellence in Energy Storage and Transportation Electrification in Hydro-Quebec, Canada. He obtained his PhD in 2003 with the highest honor in the area of material science from University of Bordeaux, France. From July 2003 to May 2019, he was working in National University of Singapore as a senior research fellow and group leader advanced batteries lab at NUS physics department. So for the last 20 years, Dr. Reddy have been working on the synthesis, characterization, and evaluation of advanced functional materials properties of cathodes, anodes, supercapacitor, and solid electrolytes for battery. So in today's lecture, we will have students from materials electronic class. Most of them are in the undergraduate students, but some of them also in the graduate studies. So for Dr. Reddy, time and screen is now yours.
Okay, thank you, Chairman. So once again, I'll put my work on it. Yeah, can you make it enable my screen?
Yes, I already enabled it.
Yeah, I think now it is coming. Wait 1 minute. Oh, sorry. What I will do is that, anyway, good morning, everybody. Okay. So slide, you're able to see all the slides? Yes?
Yes.
Yes, clear.
Okay. Again, good morning, everybody. So my name is Reddy. I think we call it very simple Reddy. So once again, thanks for Professor Herman for his kind invitation. In fact, we met in almost 13 years back when I was working doing PhD at the National University of Singapore. In fact, I can tell that some one of the good Indonesians, I think Herman is also one of the nice material scientists. Also, another area is like another close friend with Henry, work with photonic material. So what I am going to talk today is that although my talk title is a little bit, since I want to make you encourage the students, so try to make it as more simpler.
Oke, jadi hari ini kita bakal praktikum.
It is okay? Yeah. So presently, so next slide I'm going to move. So these outline of my talk, since time limitation, I'll see how much presentation I can tell accordingly. We can plan. So I'll try to go a little bit slowly. So you may see that I'm coming from Quebec. So you can see the Quebec is a place where the one of the French in Canada, where the French colony. So here we speak French and English. So mainly I can tell that, and so interestingly, so we can see compared to Indonesia, we especially here we can see extreme winter temperature almost minus 25, 35 depending on the seasons. Other things, I think all nature wise, I think you people always like in Singapore or Indonesia, we can more humid weather throughout the year we can see. So here, so these almost extreme climate we can see there's a little bit disadvantage while work with hybrid vehicles. So regarding our institute is called hydro, means research doing mainly on hydroelectricity. I think 90% of the work with the hydroelectricity project, and 10% of the work is on, we are working on the energy storage and then electrification of the vehicles. So regarding the university, so we have collaboration, strongly collaboration. In fact, since these are government institutions, we closely collaborate with McGill, and then all our PhD students are related to the McGill and Concordia. So, and some other institutions. So regarding, I think already people have talked about, I think almost I was there in nearly 12, 13, 17 years in Singapore. In fact, also I was involved in the Material Research Society Singapore with the various conference organization. Also I involved in some of the project proposals, and also especially some editorial board in the material research and the energy storage, etc. So regarding my talk, I told you that already work with the battery materials. I'm going to summarize in the next slide. So I would like to thank you. So these are the group members, starting from top row is the PhD students, and bottom you can see, I think a lot of the school students have been trained for the last 10 to 15 years. You can see the Singapore, also it is a small country, people can access very easily since it's like almost like 40-kilometer radius. Any students, you can do the project. So it was really very, very well equipped lab. That's why, and also many people can come and use the facility. So in addition to this one, the students are able to present in national and international conferences. And I think this is a nice opportunity for the students to explore in science. And also at the end, many students nowadays, I think many students have joined in the area of material science and engineering with, including Singapore as well as overseas universities. In addition, we publish various papers based on the energy and electronic related material research journals. Also, I had a nice association. In fact, long back, some people from Padijaran University, also small short-term research people have visited our laboratory, and some other Indonesian groups have visited in our laboratory. Also, we have done some small outreach groups. And also, in addition, this journey also I'm able to meet some other part of the African countries, etc. So also I'd like to thanks my previous boss and then present boss, Dr. Karim. So these are my collaboration. I think we already collaborated with various parts of the within Singapore as well as India, and also so I think already we would like to work with some of the collaboration already started with Indonesia, etc. So these are my research interest. I told you, since not much time and discuss too much details on my research area. So mainly since students are like graduate students, I want to make them a little bit more simpler way, more useful, especially how to prepare the material in terms of, I think that is very important as a material researcher. So I'm going to talk about the material research and synthesis and characterization techniques. So as we know that I think now start how people don't know how the electronic, what they call as the electronic material or electronic age is started. I'm going to briefly tell about our human history, how the materials are developed, are interrelated, starting from early started in the Stone Age, Copper Age, Bronze Age, Iron Age, and Silicon Age. I think Silicon Age made them all our electronic material. For example, a lot of electronic revolution has happened after Silicon Age. I think nowadays I can tell the advanced material age again. Although materials are same, I think people have now very sophisticated technology. I think, for example, electronics, all the materials, I think nowadays we have very sophisticated fabrication techniques. I think people can achieve with nanometer resolution materials, for example, thin film. For different electronic applications, people are able to do. So all this one, I think we learned based on from world history. Regarding the Stone Age, I think we were able to learn, for example, I think the same thing will part of maybe some remote places also, I think, or we can see those people are like part of India also. We can see that still, I think they adapted, they utilized the stones to for different applications, start as a sharp material, cut the material, or to get a fire also they use the stones. Followed by stones by the sand, I think we learned how to make a glass, followed by, I think nowadays various glasses, I think a very huge industry, ceramic industry is going on with the different decorative applications, etc. And later with the clay, what we learned from the clay, I think it is a very old technology. Then afterwards, due to clay technology, then we are able to see the how to make a vessels, and especially for the decorative application, depending on that one. Followed by, I think we have already we are able to learn the how to make a powder. They can powder mix with water to get. I think we can use the cement. So this is cement technology. Also we learned with almost like 3000 BC and all. For example, this is all what I'm telling. This is a way technology has been evolved from the old generation to new. I think nowadays there is a lot of challenge, especially cement. Cement itself, there is huge, a lot of compositional varies. I think there is extensive research, especially in terms of say, a lot of things has happened now and the worldwide. So after what is the from metals? You know, the metals. I think metals were extracted from the rocks. For example, smelting is a technology. So suppose we can you take the oxide, mix with carbon or charcoal, so to get a respective metals. I think this is very important. The way we can use these metals for the various applications. Again, the copper age or bronze age started almost like at the end we were able to learn how to make a metal bronze for different applications, followed by smelting, and we can see, for example, followed by iron age and etc. So what I'm going to give brief summarize is that due to this like previous what they call all this one nowadays, I think copper, for example, copper can be used for different electronic applications, including battery current collector, or for example, copper as a wires, etc., etc., and also copper tubes with the different applications. Again, the sometimes fibers. And regarding the iron age, already I discussed the based on the iron, and we can use the steel for different applications, starting from transportation and like construction purpose, etc. Nowadays, recently, we can, for example, people have replaced the learn with modern metal with ceramic fiber advanced material. So in general, I think later in 19, almost like vacuum tubes have been discovered. So then we'll followed by we are able to learn how to make build a computer. So due to this almost like discovery in for 1947, first transistor has been discovered, followed by, I think these, you can see the olden time they do very small demonstration. Now people can do very fantastic. They make a point type contact they can do. So this is the way I'm telling. This is the way early technology has been. The same thing happened with the lithium battery also. So next is, so due to this, I think silicon technology made them the revolution in the electronic rule. For example, you can start from iPhones. You can see a lot of changes happen now. I think again, just I would like to remember that in addition to this, our silicon technology also, I think lithium batteries are also made them revolutionize our the mobile system. I think when compared to the olden time, and now a lot of battery performance has been improved. So just I'm going to introduce how the electronic, for example, one of the electronic material also you can call it sometimes the lithium battery materials also important part of the electronic material. Although, so lithium, so here you can see the lithium batteries contain various different type of designs are there. So what people will do is that, for example, your mobile phones contains this type of the pack. Again, if it is laptop, it contains, there is a cylindrical cells, and sometimes you have your like electric vehicles contains lot of cylindrical cells are combined together to make a pack. And depending on the applications, I think people can do different big designs, etc. So later I'm going to touch up on what are the principle of this, all this one in the next slides. So you may ask you why energy storage. For example, energy is very hot area. So you want to store is in fact the electronic, for example, solar cells. So here, this material you want to store the energy. I think batteries are very important storage devices, or wind energy, or for example, to run the electric vehicles. I think batteries will play an important role. So again, I think places like in Indonesia or India, very especially major metro cities like Jakarta, I think there is huge pollution. I think people are thinking due to the due to this, I think we are getting a lot of pollution problem. I think a lot of disease also going to occur nowadays. I think places like in Canada, all over the major cities, people would like to, especially would like to reduce the vehicle pollution by using the electric vehicle as approach. Again, the cost is slightly higher. I think people are looking for another alternative approach. So you may see why this area is very famous. I think almost like 2019, I think all people might have known that Nobel Prize in chemistry is given to one of the 3 battery researcher among them. So he is Professor John Goodenough. He is both physicist as a chemist and solid state chemist. I can tell that olden time people don't call as a metallurgy all. Anyway, everything is, since the material researcher, he is able to do both the magnetism as well as lithium battery, etc. And a lot of very original work has been done, especially in terms of basic sciences, has been done at the university level. Nowadays, I think people want to research in a different way. People can do. Again, I would like to mention that in addition to this one of the French pioneering chemist from Michel Armand also, he's also one of the early researcher started in the area of the rocking chair polymer electrolyte concept. So regarding that, I discussed based on the utilities or solid materials are broadly classified into depending on application, building, and electronic material, for example, silicon, germanium, gallium arsenide. This one we call as solid state electronics or solid state ionics. Remember, solid state ionics is a very vast subject. I think it depends on us. For example, nowadays people have claimed that lithium ion batteries also, for example, you work with the solids alone, electrolyte alone is a solid state ionic. I can tell that it's like multidisciplinary. I think people can do this type of work. Again, it is a combination of material science and engineering. And energetic material and engineering material, already I mentioned, and food material and pharmaceutical, for example, biomaterial or watercolors, and also depending on the applications, people will call with a different terminology. And also based on the physical properties, we broadly classified based on metals, semiconductor, insulator. For example, if we take magnetic material, we classify into ferro, ferri, antiferro, spin glass type of the. And also depending on the optical properties, UV, IR region, transport, and then dielectric, thermal, and radioactive properties. For example, if you take any optical as an electronic material, so it should be absorption, emission, and amplification will occur, and it has a different type of application. For example, you want to see the laser. I think this material is very useful. Glass fiber, or sometimes a smart windows. For example, the electrochromic technology is one of the smart electrochromics. I think depending on the light, I think people can do the. I think these very interesting applications. People with the smart windows, especially people are running using with aeroplanes, I think the windows contain smart vehicle electrochromic application. Again, solid state ionics is the terminology, solid state with the solid state electronics. I think it deals with the materials with ions with the predominant charge carriers. Anyway, we broadly classified into the ion conductors or mixed ion conductor, etc. Again, regarding the materials, for example, since it's a multidisciplinary, I think depending on the shapes and people can use it for different applications, starting from for biomedical, nano-optics, water filtration, and for example, tissue engineering, etc. I think depending on applications, people have been nowadays, there have been a lot of materials have been, for example, you can see this type of material, maybe silicon tips, or the people can use depending on the, and also sometimes energy storage, conversion, etc. So, and also there is a huge interest, for example, in terms of, um, uh, for example, publication, as well as a huge interest through the year. So in conclusions, materials will play an important role in the area of electronics, energy, water, and healthcare. Again, energy is a very broad. You can get it energy from different sources, starting from solar, thermal, battery, wind, and mechanical hydro, and especially nuclear also one of the, okay. And especially electronic engineering is interdisciplinary. I think we need a background of chemistry, physics, and electrical and mechanical. And sometimes people also you can call as a biomedical. Suppose you want to be sensor design, I think we need a knowledge of the biomedical engineering. So this, what is our job is that try to understand how to cook the material. Maybe different ways are there. I think I'm going to summarize what are the different materials you can, how to prepare the materials. Although silicon is the main material, since silicon, we know the technology by the CVD, chemical vapor deposition techniques, also silicon can develop or by solid state or by quenching techniques people can do. So these are the various materials. For example, you can see this is a periodic table. So for example, you mix with the gallium arsenide, these all are gallium selenium. I think you can mix NP, different type of combinations, depending on that what people can do. For example, if you want to be battery material, we need a 3D transitional element. For example, nickel, cobalt, manganese, I think these are a little bit more promising, and with a combination of lithium metal and oxygen, etc. And for example, so these are the rare earth material, depending on applications, people are using the with different area. For example, if people want to be magnetic properties, like magnetic applications, etc. So in what is material science or materials, it will deal the study of the properties of material depending on the composition microstructure. Remember, all the material, for example, you want to make any properties, it will vary depending on composition, microstructure, etc. Again, microstructure will vary depending on how your own process. In general, material science and engineering deals with the structure and properties of the any material. For example, you take with the electronic material or XXX, always the same. So what is the other graduate research or anything, what you do that pick the application, for example, electronic applications or any application as well as pick what are the application, and each application, depending on application, we need a different properties. For example, electrical, thermal, magnetic, optical, and then mechanical properties. Again, identify the material, for example, depending on structure of things, and then process the things and try to understand the overall shapes. For example, you can do the metallurgy approach, either casting, refining, or reduction, or vapor decomposition, or annealing, or etc. You can do. So also one more the slides I'm going to talk, suppose sometimes we call it some nano regime. For example, usually nano means you start from 1 to 100 nanometer. Submicron size we call as something above 1 micron, or like 100 nanometers to a few micron size. So remember, nanomaterials, these are range. You can again, sometimes too small size is very difficult to scale up. So remember, sometimes, although it depends on terminology, some application people will call as 50 nanometers also, or sometimes for biomedical applications, they want really nano size, maybe 2 to 3 nanometer or below 5 nanometers needed with the uniform particles. Again, for example, water purification or biomedical, or for example, photocatalysis or any solar cells, I think we need a particles with a uniform size, with almost like very smaller particle is good, and we need high surface area. These are the basic things we needed. Another thing is the materials. We also need to remember, so property of any material will differ from the bulk. Nanoscale will be different when compared to the bulk material. Again, especially for miniaturized devices, including that they were all electronic gadgets, I think they're almost like nanosize. For example, silicon, particular things almost like nano coating or nano layer coating they can do. Or sometimes in magnetic discs also they have something like they coated it's almost like thin layer of the material. So this is a way we can use various type of nanoparticle plates, rods, strips, porous materials, or fiber cells. Also, we can use it for different type of electronic applications, or you can use it as a different type of, depending on application, people can get the materials. Again, for example, you may ask either what is silicon chips. I think silicon chips technology is different. I think they use silicon metal alone. I think fabrication, they use the physical vapor deposition techniques or chemical vapor deposition techniques they will use. For example, if you take a carbon-based materials, again, so for example, these are silicon nanowires. I think people have been reported with the CVD technique. And anyway, I'm telling the overall summary is that, so these are, so in some particular case, I think they prepare a silicon mold and they can grow with what they call as by electron etching technology or synchrotron radiation. Insert a particular radiation, they put a mask and they can prepare silicon arrays for depending on the applications, especially for the electronic applications, etc. So this is a way you can prepare the material. You can start from various chemical routes. I think these are the materials or material scientists, these people can think about this one. Or depending on the sophisticated techniques with thin films, people can use by the either physical vapor deposition techniques or chemical vapor deposition technique. Again, physical vapor deposition broadly classified based on the RF sputtering, pulse laser, atomic layer. I think I'm going to tell about different type of the technique. So since I think it is very important, although people want to design any new material or anything, suppose if you take an oxides, always you have to worry about the oxidation state and charges to match. So it means that if you prepare any material or any new design, I think we have to worry about the oxidation state it has to match. Then only we're able to get either doping or anything you can do. So regarding characterization techniques are concerned, I think X-ray, I think all metallurgists or material students, you know the principle of X-ray. X-ray is very finger-free. Without X-ray, I think we cannot survive. That is very important. So especially we'll give the information what is the impurity of phases, or is pure or not, or we'll get some lattice information, especially battery material if you want. I think we can see the cation mixing, means lithium is going to another side or not. This way we can tell. Or sometimes we have light elements like lithium. For their more structural information, we need a neutron diffraction, and sometimes X-ray diffraction techniques, for example, X-ray absorption. And these are all more fancy techniques. Still, I think you have real XRD, that will be enough for you to you want to start any master's project. I think X-ray will be more than easier. I think you are able to access within your university, in your department. I think that way it is not a problem. I think you can do. And still, if it's a new material, very promising, you can do collaboration, especially this place. Or we have near, I think Batam is also, there is a nuclear energy center. I think we can do some studies there also. Again, if you have thin film, people are working with thin film. I think based on my experience, my PhD work I did with Rutherford backscattering spectroscopy, I think it's a very useful tool to understand the composition thickness, because thin films are very thin, very too small size. I think we need a sophisticated technique to know the exact composition thickness. And it is a way, for example, you can tell the silicon is there. What is the real problem? Silicon, a lot of defects, everything, if electronic material, I think RBS is a good technique to understand the composition thickness of the material. Next one is the nuclear reactions. Again, they used a helium beam, react with lithium to get a nuclear reactions, again to know the content of the lithium, and sometimes Auger spectroscopy to give the information homogeneity of thin film as well as composition, and X-ray photoelectron spectroscopy. This, I think this technique is known to know the type of oxidation state, for example, is depending on the materials. And for example, silicon, what is really silicon is, sometimes there is oxidation of silicon surface, or something is electronic material surface is oxidized or not. I think that way, I think XPS people are going to use very sophisticated technique. Regarding, for example, morphology, I think people can use the scanning electron microscope, and sometimes, especially AFM is atomic force microscope is very important. Suppose you make electronic, any electronic circuits, I think they would like to see the surface is homogeneous or not, or roughness, what they call root mean squared roughness values. It is very important, especially for the, to make a, especially in silicon electronic circuits, I think they need surface. So for that case, I think people, they use atomic spec microscopy to see the surface roughness. Again, TEM and transmission electron microscopy just to see if your material is nano size or not. I think this is depending on the applications. And another techniques, for example, you want to do with the magnetic means, since we know that some materials are magnetic also, just based on the application people can study. And TGA, DTA, and IR, Raman, for example, people are working with the graphene research. I think their Raman spectroscopy is very useful to understand the what type of bands are, etc. And if it is a bulk material, for example, lithium battery, or for example, surface area is very important. Suppose you work with the solar cells, I think we have to know the surface area. For example, my materials are very porous or not, or high surface area, like Bernard-Emmett-Teller equation. It will give the information on the surface area of the material. And sometimes density. I think nowadays density, not many people are going to report, since we are the old generation solid state chemist. I think I can tell that if you work with solids, density is also one of the physical quantity. I think we have to compare the density obtained by the experimentally and theoretically from the XRD. We have to compare. That is very useful. And at the end, if it's the electronic testing, I think, for example, is a galvanostat, potentiostat, or impedance analyzer. I think this is very useful. You work with the solar cells or electronic circuits. For example, you want to see, understand the, what the usually, if you go for electronic industry or silicon industry, so they use this impedance analyzer to see the what type of circuit is happening. For example, you get one semicircle, and you can make a one what they call a resistor capacitor combination. You can do some modeling and what is going to happening about the resistance, etc., etc. So these are all the things we are going to study in more depth, since for you as a layman, just these are all the techniques we are going to utilize it for the um, various applications. So regarding the chemical synthesis, for example, if you sometimes there's a way of preparation of material. For example, I don't want to go for high expensive equipment. You take a small beaker and do the research in the lab, and you can do various type of chemical methods, starting from sol gel, co-precipitation, and microwave, electrodeposition, and salvo thermal electrolysis. These are all things, electrospinning techniques we are going to adopt. So one example, I'm going to tell molten salt synthesis. I think this is a technique, is I can tell is simple and versatile technique to obtain highly crystalline, pure, and mixed oxides. Layered intercalation host, if you want to do catalysis or etc., are depending on the applications. Again, usually molten medium, for example, reactions are controlled by chemical equilibria, process much faster than diffusion controlled solid state. And then it means that what will happen, the mechanism is that these are the solids at room temperature. When heat at a particular temperature, since we use excess salt, it becomes liquid. So at a particular temperature, it becomes melt uniformly. While doing slow cooling, automatically during recrystallization, we will get a desired phase. For example, you want to prepare titanium dioxide. We need a titanium oxysulfate as a salt, and you can use lithium nitrate, lithium chloride as a, here is the molten salt, and put it in alumina crucible, heat at various temperature, wash with water, and we get it. This is very important. We have to use excess salt, we have to get rid of that one, and finally we can get a desired ceramic, for example, semiconducting material, electronic material, for example. Similar way, if you want to prepare SNO2, I think people want to be sensor applications. Exactly same way you can do. You take a tin containing salt followed by molten salt. I'm going to touch up about what type of different salt depending on temperature. So that will be useful in the next slide. In summary, I think this is one of the iron oxide you want to prepare. You can put in alumina crucible, wash with water, and filter, and we get it, put it in the oven. So this is a way you can do. You don't need any expensive equipment to do the project in the either master's or bachelor's level. So in summary, with the molten salt technique, I think still you want to play the morphology. Depending on the material, depending on the composition, we can see difference in the morphology. Or you want to be, for example, titanium dioxide, you can take almost like uniform spherical particles with nano-sized materials you can prepare. So this is a summary. I think you can prepare a lot of the oxides, either battery materials, or for example, titanium dioxide is one of the well-known material people want to be the photocatalysis, or biomedical applications, or solar cells. I think titanium dioxide is well known. In fact, I already mentioned that if you took lithium nitrate, lithium chloride, titanium sulfate, salt at 280 degree, this is a melting temperature. The salt go there nearly to that plus or minus 5 degree melting temperature salt, and try to understand the, for example, as a batteries, people were interested in battery, we can use the same material for solar cells or sensors, or you want to dope the nitrogen, if you put some nitrogen containing sample, or for example, you put the urea, we can get a nitrogen containing TiO2. In summary, I think still similarly, I told you that we can prepare titanium dioxide or any magnetic people. For example, people are working in the magnetic materials. I think people, again, this is a way you can prepare with zinc iron oxide or lot of compounds we can prepare. In summary, I think this is a versatile method. You can, although this is a little bit not materials are known, this method is not explored. That's why we are able to, it's very simple. This is all most of the work I think we did repeated work with high school kids. I think that way, I think people can reproduce and also you can prepare the material in a large scale. Again, we asked the garnet is a ceramic material. Again, the garnet-based electrolyte seems to be not promising. Why? Because if you use excess proton exchange will occur, so some little bit difficulty while working with molten salt approach with a solid state battery, for example. Okay. So one example I'm going to tell about what is the TiO2. I think we know that titanium dioxide already discussed various electronic applications. For example, if people want to be electrochromic applications, solar cells, battery, photocatalysis, or paint, or for example, water splitting, also biomedical, etc., etc. People have been, in fact, there are a lot of application. So people are using the titanium, and also, for example, your sunscreen. All these applications they want to be nano titanium dioxide. So in general, I think I told you that titanium dioxide you can prepare you by using this molten salt with that nearly 280 degree, almost like 200 meter square surface area we can get. Again, the beauty of this sample is that depending, we can optimize this one depending on the, and also we can see the lattice parameter. So the surface area is going to decrease with respect to temperature. Is we know that any ceramic material, heat further shrinkage of the particle will occur, as consequence particle will expand. I think that is a very well-known explanation. So again, these are excited diffraction patterns to clearly show that when it becomes a nano size, we can see broad lines we can see when compared to the, if it is a click bit crystalline and semi-crystalline, crystalline, depending on crystallinity, we are able to see a nice splitted one. Again, remember, titanium dioxide is also like polymorph. It is a anatase phase, the low temperature phase. If it is rutile phase, is a tetragonal phase. So again, people can do the TEM, depending on that one, people can see the particle size, etc. In one summary, I'm going to tell you that with also titanium dioxide, people can use a different application. I think early demonstrated TiO2, people can use it for the DSC, but anyway, a lot of extensive literatures are there. Just we compare TiO2 with P25 with commercials, and still some improvement in the, what they call a solar cell efficiency. Yeah. Again, we can do another like for electronic materials by tin oxide, NB2O5, etc. Again, so for the first time, I think there's a literature. I think people have been based on the TiO2. The cells have been already with nanoelectronic devices. People have been demonstrated. So these are nano TiO2. Again, in summary, followed by, I think recently, I think 2019, another interesting material is the perovskite based solar cells has been come into the picture. Again, you can see almost like earlier started was the efficiency was lower. I think keep on, there is a lot of optimization, everything is happened. Still, I think major challenge, especially lead based halides. I think now people, I think there is extends a lot of challenges, efficiency is improved. Although since we are doing academic at the end, if you go for industry, I think there are a lot of challenges. For example, lead is a toxic one you to reduce. Still, maybe some application people, they may not worry too much, still a little bit toxic. And it is halides a little bit stability of this material. also. Anyway, there is a lot of extensive research is going on optimization. Since I'm not really going too much depth on that one, still this is a way as a researcher, I think people do some small early report followed by people improving. And at the end, you can see a lot of electronic devices have been with a large scale. Similarly, like graphene, because first time they started the work on graphene, I think there is extensive, after getting Nobel Prize, I think a lot of extensive research is going on. Although remember, graphene is, battery researcher is known from the law more than 50, 60, like 50 years back, graphene, graphite, and explanation already known. Only thing, though, the people, they're not calling that like graphene or like that nowadays. In the sense, if physicists will come into picture, I think people have been, the area has been grown like extensively. In summary, the next example is I'm going to tell that since this may common material as electronic material, again solar tin oxide, if people can use it for the sensor, solar cells, again battery, photocatalyst, paint, etc. Why? Because remember, tin oxide and the titanium dioxide, these are the semiconducting material. How do you tell semiconducting material? Best way is see the color. After preparing the material, this is almost like white in color, so clearly indicate that these are like semiconducting materials. Again, with the molten salt approach, suppose you want to be do picture research, people can do this type of various salts. Again, depending on temperature, people can prepare. Again, remember, you can fix the temperature to lower also. In order to be 3 hours, you can start from 10 minutes, 30 minutes also you can do. Since this is a way you can optimize the, what they call, you want to be smaller size, you can reduce the time, or you want to be a little bit bigger size, slightly increase the more time, or medium, you have to optimize the things. So again, this is a way as I'm summarizing. So again, if you want to make a battery, I'm going to touch up later how to fabricate the real cells. So that way, that one I'm going to tell in the next slide. In summary, so best way that you're a graduate students, how do you tell that it is nano size or not? If you do X-ray, so you can see the nano size material, the lines are very broad and clearly indicate these materials. Like I call full width of maxima very broadened when compared to the crystalline. We can see this length is a little bit, FWHM is sharper. So this is a way you can tell exactly with the Rydberg refinement. We know that, for example, tin oxide with this temperature is 3.2 nanometer and 450-degree prepared sample is 8 nanometer and crystallite side is 54 nanometer when you prepare sample 650. It clearly tells that for a material researcher, X-ray is a fingerprint. Also, we can get a lot of lattice parameter as well as. So remember, so you don't need to go for expensive technique like TEM, because unless your properties are really excellent, you can do really, you can go for TEM. Without going TEM, you can tell that, oh, so my prepared materials are approximately almost like this range, you can tell. So this way, as a material researcher, still the technique X-ray is a useful technique you can do in a different way, different, for example, depending on expertise, interpretation, people can do with a different style. Again, TEM, it just shows the samples are nano size. Still, you can expand it to get the individual nanoparticle, etc. So in summary, I think we can go for copper oxide. For example, again, copper oxide is also known. So you can take the copper oxide, you can prepare the materials with a different crystal structure. Again, this in summary, and also again, this particle is slightly bigger because of the molten salt approach, and funny sometimes some nanostructure materials with high resolution with slightly at higher temperature we can see by using this approach. And also sometimes people want to be in magnetic material approach, people want to do, for example, you want to prepare, for example, iron oxide or zinc iron oxide, you can prepare, for example, Ab2O4 with replace the various metals, and you can prepare. One example is either, suppose, for example, either zinc oxide or copper cobalt oxide or copper CuFe2O4. So this is a way you can do similar with the same approach. You can prepare with respect to the, you vary the salt, for example, cobalt salt will do, or for example, you can different salt and you fix this molten salt with respect to salts also. Okay, so these XRD patterns to clearly indicate the information about the what is going to happening. So again some nanomaterials, it will give you the information about the what is going to be the spherical or not. With the TEM information, you'll get the particle size, or sometimes If it is a rings are little depending on the particle size. If it is crystalline material, or if it is in what they call amorphous, we don't see this type of rings. Okay, if it is more crystalline, we'll get dot type of the patterns we can see. So in summary, if you got another type of the electronic material, for example, is the well-known lithium cobalt oxide that is using for mobile phones. I'm going to touch up how to prepare this one. Again, similar approach, you can do cobalt salts with the lithium containing salt, you can prepare. Again, you can play with. Again, remember here, we don't need a nano size, we need a micron size because the samples are prepared high temperature. So remember, so usually for batteries, so you may ask, why don't you look for low temperature? This is not possible. So there is a little bit, always we will get a smaller size materials. In summary, since you get any nanomaterial or any material, so the for electronic application, for example, you want to run the battery, or if, for example, you want to at the end, if you are going for the to do a job, so suppose for example, they're going to give price. If you're an engineer, so you don't do all the steps, or you buy the powder from the where is some industry factory, since you can buy them a powder, and people they're going to fabricate the, for example, your mobile phone battery, one particular industry people can do, or sometimes 18650 cells, depending on that one. So summary is that with based on the knowledge of the synthesis, what you're learning, and if you're going to industry, people are using this. So for example, you want to prepare battery material, it takes 78% active material, 58% of the conducting carbon, and PVDF is a binder. So this also like it should be, it is nice addition, and then and it on the current collector. For example, we use copper as a current collector, we can use this type of substrate. Finally, coat the sample, and roller is the things, you make good addition. Finally, we make a button cells of cells, and we can put it in the vacuum. So remember, for example, if is a suppose one person, if you suppose if you is the electronic industry, for example, silicon chips, they're doing again their fabrication technology. For example, say IC chips will be different. Again, the same industry people are working the batteries. Again, the battery will adopt this one. So it is a way. Although sometimes nowadays I think people will not do all the assembly, all including mobile phones in a single place. I think what they will do is that people will buy battery from some other company. Only thing they will give a particular specification at the IC chips with particular things, and then all to bring together. Then assembly also people can do it in a different way. People can do. So in summary, so I'm going to tell about suppose simple coin cells. Once you understand this one and see the performance of the any electronic material, I think people can do large scale batteries. So remember, so you take a material like this one, for example, is a cathode material, put it here, and separator and lithium metal and finally top cap, and finally press the cell like coin cell. This type of small button cells, I think a lot of commercially available in the market also. Again, it will vary depending on which is the voltage. That's why some cases you may see 3 volts, and sometimes you may see the 3.7 volts. Means at the time, if it is the voltage is higher, depending on the application, maybe cost is also slightly higher. I'll tell you how to tell the how do you know 3 volts, 4 volts or not, maybe next slide. So that will be very useful for your just for in terms of knowledge gaining. So usually, for example, industry, what they do, everything is mechanical. That since they're preparing the tons of the quantity, there is a mixer mixing the sample, followed by coating and drying. Everything due to automation, followed by calendaring, means just you put the sample, roll it, and cutting this, for example, depending on application, they can cut the mold and different types of this one, and sealing. For example, you want to stacking and welding, and followed by filling the electrolyte, and then aging, and do quality control, etc. So yeah, I told you already discussed, these are various type of designs that are inside. These are the only you will see only positive, negative. I'm going to tell about next what is there inside. Suppose if you want to be any electronic material or any electronic material laboratory, I think some techniques may be same. For example, you need a impedance analyzer. I think this technique is very useful if you want to be electronic circuits. So what is going to happening if depending on resistance response, people can see your circuit is okay or not. Or sometimes people want to work with the lithium batteries, but they need a galvanostat. So we need a lot of channels to try to understand this one. Or sometimes he's a really solid state engineer, solid state electronic engineer. I want to be conductivity to the solids, for example, multiferric, or in different applications. I think their conductivity, so there people can use a different type of conductivity setup. And sometimes if a hygroscopic sample, we need a argon-filled glove box. In summary, so for example, if you take any material or any battery, best way is that how to calculate the capacity. Capacity is nothing but how much time is taken from 1 voltage to out voltage, followed by then multiplied by current divided by mass of the material. This gives the information of capacity. For example, you wanted to see the what they call energy density. Energy density is nothing but what are the capacity. For example, the voltage is very important. The difference between cathode minus anode is the voltage of the cell. So usually higher the voltage is good. So at the end we will get a higher energy density. Voltage multiplied by capacity, we will get higher capacity, and we can do a lot of other things like diffusion coefficient, etc. etc. Another important characteristics of any electronic material or anything, just we need a cyclic quantumograms. This technique is very useful to see, for example, if it is reversible or not. As a layman, we have to get a positive, negative current. It clearly indicates that this material is reversible or not. Still, you can do more basics. Since these are all the things you're going to do more detail in this one. Still, as a layman, I think we have to get a reversible peaks. Clearly indicate this material is very useful. And I think this slide is very useful. Suppose if you work with the electronic industry, I think people may see that notations may be different. I think resistor, and it is a constant phase element, they will use a capacitor. And depending on the circuit, there is a lot of complex modeling. This is called as electronic engineers, electrical engineer. I think different depending on the circuits, depending on the interpretation, people can use what they call a resistor, plus capacitor combination, or inductor. And then, for example, Warburg or some different type of resistors people can use. Since as a battery terminology, what we call as a high frequency region is electrolyte one, and charge transfer, we can see the how, for example, one lithium ion move from one side to another side, there is charge transfer occurs due to electrolyte interface, and bulk sometimes due to the electronic conductive active material, pore spilled in the composite, etc. So once you get a pattern, we can do some complex modeling. For example, as a physicist or electronic engineers, people can do. So how to see the, how to interpret the spectrum. I think by modeling, we can get the information about what is the exact resistance or exact capacitance or inductance, etc., etc. People can do. Overall summary, the impedance values are sensitive to the voltage, cycle number, everything. Again, it is related more specific and you go for the more depth into the particular research. Again, these are simple electronic circuits. You can see people can do resistance, capacitor, or constant phase elements. Sometimes your electronic, usually if you go for electronic industry, always they use a capacitor. The reason is the most of the electrodes are, if you do the alpha value, almost like smooth surface. At the end, they can use, if it's alpha value close to 1, I think then we have to use the real capacitor. So anyway, I think these are all the things. Once you go more deep, more detail in depth, particular area if you go, I think people can understand more depth. Still, this is a way for you. It is nice to understand the what is the meaning of electrical equivalent circuits while doing with, for example, any electronic circuits. So I told you the one of the electronic, I told you positive means these are cathodes, anode, and electrolyte material. People can do the literature. So a lot of the electronic cathode materials are reported in the literature. I think one example, since there is too many numbers are there. One example I tell you how to what they call it, how to get the information. For example, so if you do any electronic material, any battery material, always you to look for the Plato. See, for example, lithium iron phosphate is 3.5, cobalt oxide is 3.2, and lithium iron phosphate means higher voltage is the way, best way is a good. At the end, we'll get higher capacity. Remember, voltage of cell is difference between the cathode minus anode. For example, 3.2. Here you can see 3.2 volts minus 0.25. Or some particular, just now you read 3 volt battery. 3 volt battery is nothing but, for example, here is around 3.4 minus 0.25, somewhere this battery. So that way, depending on the cathode, higher the voltage, then automatically, for example, 4 volts or 4.2 volts. So the cathode chemistry is different, and sometimes they'll get more energy density. That's why nowadays some mobile phones, like depending on company, I think last longer time when compared to the like old and more than 4 to 5. It means there is a huge in what they call as technology modification is happened within the battery industry. Again, cost has been still is reducing. Still, people are expecting to reduce further. So this is one example. Once you make a battery fabrication, we waited for nearly 6 months, reasonably almost good stability and good close to the good thermal stability with respect to the lithium iron phosphate. Also, you may ask you that why don't you use with lithium is very expensive. Why can't you use the sodium? Yes, you can do. Again, remember the voltage will be lower. For the applications, for any battery, if you go for battery engineer, so they look for okay, any good material you have to get higher potential. Oh, this is good. So although this is getting high capacity, maybe stationary application may be good. For the same material, just replaced by lithium by sodium, again the voltage is nearly 3.5. So that's why it is very important to understand the basics of this one. Again, already discussed about this cathode electrolyte materials, because again the ceramic engineering is also playing an important role. Again, if you take a ceramic material for electrolyte, I think we need a sintered pellet. Problem is high temperature. Again, these are a little bit drawbacks with if we make fabrication of the all solid state batteries. So another method, what we call as the carbon graphenothermal reduction method. Suppose if you want to prepare the materials by using carbon, already discussed about the previous early history, to take a metal oxides with respect to carbon, depending on the there is how much carbon you want to reduce. For example, here you can do 2 carbon, is to use a 2 carbon to get a respective molybdenum is in 4 place. I think you can be able to prepare the various type of the metal cluster compounds in a. Again, remember we need a tube furnace with argon for tube facility. I think that will be very good for the to prepare the materials in a way. Again, I think I already discussed this solid-metal approach. Also, you want to prepare an iron oxide. Remember, iron metal, if you too much carbon, you can put automatically with iron metal. Iron oxide is iron is in 2 place. Accordingly, we can optimize it with respect to carbon. We can get iron oxide. So in summary, depending on carbon, depending on temperature, still we can get a different type of the phases. Again, these materials are magnetic. For example, Fe3O4, people are using for the magnetic applications. In summary, you want to be graphenothermal, if you want to be RGO and reduce, remember we need nearly 650 to 750 degrees temperature in it to react the carbon to reduce the metal oxide to during this temperature. So this is a summary. So as an example, the graphene is one of the fascinating material people have been looking. Also, we look at again, graphite is almost like Flato is really good. So graphene seems to be not so. Although we get high capacity, in reality, this material may not be too much promising for the battery. Still, because of the size surface area, I think people are using for various electronic applications. For example, other applications like supercapacitor, etc., etc. So in summary, although you get slightly 1000 milliamps, I think this material may not be promising. So graphite seems to be still, we cannot replace the graphite, although graphene climb only with a just like few surface layer or what they call as graphene coating or PVs. So in summary, I think people, if you want to explore still other applications, graphene waste derivatives, for example, you want to use solar cells or electrode, drug delivery and wastewater treatment, and especially sensors and different type of example storage. Already I talked, graphene alone cannot use, only just as a graphene as a coating layer to use for different applications. Again, remember this technique for again, if people want to use a co-precipitation, this is also one of the technique people are utilizing in the electronic industry, for example, battery industry. People, this technology, people have been prepared nearly tons of the quantity, although in the lab scale, people have prepared in the burette and the beaker. We can precipitate the materials by mixing, if we take any respective hydroxide and chloride, precipitate that one, filter the things and heat the sample. So the beauty of this co-precipitation method is if you have 2 to 3 elements are there, homogeneous mixing followed by precipitation. So it is very easier. So whereas in solid state, for example, nickel, cobalt, manganese, so you mix with the 80, 10, 10 or 60, 20, 20, 20 composition. If you mix with solid state method, it will not work. That's why already people have been demonstrated. So best way to prepare this one is just to precipitate in the atomic mixing in a small level. So this technique may be really useful for the real application. So this is a way of the electronic material. For example, you want to prepare in a large scale. I think this is really demonstrated in the industrial. I think nowadays people in Belgium, there is extensive nearly tons of the quantities people. In summary, I think people in a lab scale, people want to play pH, concentration, and especially salt. Also, you can play with depending on the morphology and composition of the sample. So another way is the combustion method. Suppose if you want to be, for example, Indonesia, we have a lot of fuels or natural resource, natural containing material. So you can use that as an approach to use a naturally occurring material. I think people can, people can use it as oxidizer and to get a uh, um, to try to use the material as a what they call as urea final at the end. Sometimes and within a small beaker and a hot plate, you're able to prepare the materials in the nanoscale, and you are able to get a respective desired dark color product at a room temperature at doing the hot plate. Again, various type of the citric, different type of sources you can use, starting from citric acid, tartaric acid, urea, all of polymer, malic acid. There are different size sources people can use. Another technique is electrospinning. So usually people, what they will do is they mix any polymeric layer, for example, titanium dioxide dissolved in any polymer, and pass through the small niche, apply with high voltage. So as a consequence, they're able to get a fiber type morphology, or depending on the polymer, sometimes they may get different type of shapes also possible. Again, this technique people want to prepare in a large, as for example, one of the battery materials also people can demonstrate it. Using this approach, we're able to you're able to prepare some respective type of different type of oxides. For example, you want to prepare oxides or titanium dioxide or titanium oxide, etc. Suppose some specific application, for example, people wants to be electrocatalysis or some other application, they want to be used as a electrospinning mat on the nanoparticle. So they want to be electrospinning and spraying, like one sprayer we needed. So at the beauty of this technique is that the small nanoparticles on the surface are some specific application, for example, biomedical. So they want to be some particular things they have to spray it after the electrospinning mat. So for that applications, they need a different type of electronic application. They need a different way of setup. So in summary, I think people can do at the end. People have been already demonstrated electrospinning. For example, people can get a lot of the fibers, and sometimes recently people are climbing that with the mask also with the electrospinning technology. I think people have been especially filtration, that's why especially from bacteria, a lot of things, a lot of improvement has been done in the recent literature. Again, people wants to prepare fiber material, for example, tissue engineering, for example, nanograph technology. These are all things with electronic, for example, biomedical applications. People use demonstrated use of the electrospinning technique. And sometimes people want to be a spraying technique, for example, a large scale synthesis. People want to be, for example, water purification or a big large scale application. They need a big spray, uniform particle, sprayed particle. They use a sprayed pyrolysis technique. They took a respective salt, pumped by using the what they call a sprayer, nozzle, and then is the furnace. During this temperature, we can get, they're all optimization nowadays, not so simple. I think people have been demonstrated. These are the oxides we can do, etc. That and the different type of oxides people can demonstrate it. Again, as a mechanical engineer or a metallurgical engineers, people want to prepare any composite, nanocomposites. I think people, they can use the ball milling approach. So ball milling is nothing but you take any metal oxide or any metallurgist, for example, you can take the materials mixed together, put it in a ball, respective ball or agate or this stainless steel, and by using mechanical mixing or vibration with depending on the time, you can prepare the materials in the nanoscale. So recently, I think people have been adapted with the use of the magneto ball milling approach. At the consequence, they're able to people can prepare the materials in the nanoscale. So another approach people have been, again, people wants to prepare in the composite, example, tin, etc. People want to mix it. I think we can use this approach. So one way is the micron size to nano size means by mixing ball milling approach, where we can see the clearly nano broadening of the line clearly indicate that your materials are a little bit nano size, and nanocrystalline, we can see the difference in the TM pattern, etc. Again, remember hydrothermal approach, solvothermal being. In fact, suppose, for example, you want iron phosphate is one of the electronic material people are using. I think their material should be nano size with a carbon coating. I think people have been already demonstrated in industry, large scale hydrothermal and solvothermal reactors use it for the production of the lithium iron phosphate. So I think this is the way people use this, the small scale. People have been what they call a scale up by using the industry. And sometimes people want to prepare hydrothermal, we want to be crystals. These are different type of the materials people can do. And these are one example. Still a lot of things is going to be happening. Suppose, for example, people want to be solar cell, or for example, sensors or supercapacitor. People, they use it, or electrocatalysis. So they coat this material in nickel mesh, dip the sample in respective salts. Finally, heat it depending on temperature, we'll get respective metal oxides. So again, we can study the morphology or to see the contact. Depending on applications, people can study the, especially we don't, sometimes most of the time people they climb that very high surface area according to the nickel mesh. In reality, we did the experiment. So I don't think much high surface, only reality that in terms of aerial wise, surface area is good. The real surface area is not very high when compared to the bulk material. So it depends really what people are climbing, that sometimes is okay. So in summary, what we learned based on the applications, different pore size and surface area is needed depending on application to applications, etc. So I'm going to skip. Another one is the nitrates. It's very important. For example, chromium nitrate, titanium nitrate. For example, this is one of the gallium nitrates, but they're all electronic applications because nitrates are very hard, and particular applications, nitrates are very promising because once it forms, nitrogen metal bond will form, then it is very stable. So as a consequence, I think the battery research we explored because of we are interested about 3 lithium get reacted compared to the oxides. Still, there is a challenge, especially in terms, although we climb some nanomaterial seems to be promising. In reality, for the in terms of the what they call capacity wise, not so very high. So potential is a little bit low. That's why we not much interest on this material. Again, if you have the Rutherford backscattering spectroscopy, it will give the information about, for example, cobalt and nitrogen film and SiO2. So these are all characterization technique. For example, there are all things I think industry may not be interested. Still, I think they will worry about particular things already standardized one they can give. Still, as we do with the research, I think these techniques are very useful to understand the. And sometimes you can do some X-ray absorption to see the what is cobalt is in 3+ or not. Depending on oxidation, we can see the edge. We'll see that with particular oxidation or not. Or if you want to take an oxide, pass with ammonia gas, we'll get respective nitrates. This is the way the bulk material can prepare. So another materials, thermoelectric materials. We know that thermoelectric materials have different applications. For example, is a well-known thermoelectric materials are the antimony telluride, and these are the, for example, these are a very promising one. So anyway, still because academic research is going on, so at the end people can do different doping, different type of new compounds can prepare. So overall summary, I think any thermoelectric material should be, I think people can use it for different applications, starting from air conditioning and spot cooling for electronic chips. I think this is very important because we want this also thermoelectric material is very important if you do with any electronic engineered material, and superconductors and thermal and also waste recovery, etc., and geothermal water applications. I think so. Again, in summary, I think materials will play an important. Without material or anything, we cannot do. All are interdisciplinary. So regarding the synthesis of thermoelectric material, remember, usually a thermoelectric material is here. For example, if I talked about the oxides, you want to prepare the oxide, we need oxygen. Here, these are the thermoelectric means we have to avoid the oxygen. So remember, any thermoelectric material always try to, in a closed reaction, for example, put the sample in a sealed quartz tube and heat the sample, we can get a respective. So it is what they call a solid state conventional solid state reaction by mixing the initial amount of any element. For example, I'll tell you some particular elements. All an element, no oxides, and subject to the heat treatment, promote the example at a particular temperature becomes liquid. and sometimes quenching will be there. Again, I think people want to further like hydrotherms, only initial mixing, people have been adopted different approach. Again, remember I told you that we need a quartz tube because these are all the thermoelectric material you want to prepare. A quartz tube is needed, and also you have to seal the properly. And another interesting thing is that heating rate, all this take into consideration. And sometimes, for example, this they are air sensitive. We need a glove box, for example, or any nitrogen. It depends if materials is not sensitive. You can work nitrogen filled glove box or organ filled glove box. So again, the beauty of this, for example, depending on applications, I think sinterability is very important. In thermoelectric material, you have to again further press by using hot press or like spark plasma sintering. So this technology just you have to make you, for example, any ceramic material, you press it to make a sintered pellet. I think these are techniques people are going to use it for the thermoelectric applications. Just I'm going to see how much time is there. Okay. Another one is, for example, these are the different types of formula. Again, in summary, people, academic researcher, people can do different type of the mixing are possible. So this is almost like in thermoelectric material is started in 1960. You can see, for example, silver, lead, this composition followed by silicon, germanium, nano silicon, germanium. In fact, you can see there is a lot of, for example, you can see tin sulfide also will discovered, lead sulfide, and lead selenide, copper sulfide. Although at the time, I think, well, maybe why at the time people have been see that depending on the stability or depending on the technology, I think they look into the okay, and also the response. So these are the, for example, the old and new. So we need the various combination. Recently, people have been looking into this one. So another example, for example, you want to be smart card. I think we need an electronic material, electronic devices to work in the almost like a 10 micrometer size. For example, you want to work attached to the couple of the battery, either same thing what I talked about in the coating. You can use a sputtering technique or any PLD, any technique to make a layer by layer, cathode, electrolyte, anode, and finally protect these things. All the cell is almost 10 micrometer size. That's why we call it nanoelectronics. So we need the try to understand this one. In summary, so what is the beauty of this technique is that suppose you replace by stainless steel or glass substrate by ITO, for example, Indian tin oxide transparent substrate, and you can do same, for example, tungsten oxide, titanium dioxide, thin films. You can do, or in vanadium nickel containing compound, you can do electrochromics. For example, you can apply the voltage with electrolyte. We can see the color change of this one. Also, sometimes, for example, you can use metal oxide, tungsten oxide, titanium dioxide, or if you use organic molecules and conducting polymers, people can use it for the thermoelectric media, for example, electrochromic applications. So again, so these electrochromic applications featured in the smart windows and electron EC displays. And for example, I think nowadays you can use all Dreamliner flights also. They especially if you press that window, so they can see sometimes the electrochromic windows is going to appear because color will change by pressing the particular button. I think what is again the summary is that again same electrochemistry. For example, what is happening is that tungsten is 6 is reducing to, for example, tungsten 6 is reducing to, or the oxidation stage just is going to change with respect to the either lithium or proton exchange. Another way is that, for example, Persian blue and different type of the polymers are the examples. Suppose conducting polymer based on the EC means conducting polymers. So with a different type of the examples. And another variety is electrochromic material based thiophene based polymers. So for example, this also, so anyway, each depending on the applications response will be different. And anyway, more details if you do different, for example, if you're organic chemist, I think people can design, or polymer chemist, we can design the different type of molecules. Still we can do a lot of basics. As sometimes your performance is really promising. I think people can use it for the different applications. In summary, another application is the PDOT, means this is also one of the polyethyl people are using by various applications, not only electrochromic and other applications, for example, solar cells also people are going to order. So these are P dot containing materials have been already reported with the various electronic applications. So again, so remember the summary is that we can do depending on the what they call as conduct potential, and then band gap. Each materials have different type of the what they call as band gap, etc. So this summary, if you want to be electrochemist, you need you want to lab scale, you can do platinum electrode or a reference electrode, and you can use your electrochromic material coated on either any coated substrate. You can see the real-time monitoring change of the color. Just visually you can see the things. Regarding sensors are concerned, I think sensors have very different type of applications, starting from automotive, food industry, agriculture, medical. For example, medical, we need oxygen, glucose, and water treatment, and environment application like SO2, CO2, NOx. I think, but in industry, I think this is needed. And especially industry carbon monoxide, I think people are working with iron industry. I think there is a carbon monoxide is also going poisoning. For example, to put a lot of metallurgy in this carbon monoxide, they need a sensor. Make sure that all the workers are doing well. So make sure that they're in a proper concentration of carbon monoxide. And is there any leak? I think people can test by using this sensor is also play an important role. And for example, steel industry means steel like iron is already shown there, aerospace, especially humidity sensor, etc. And also petrochemical industry. So again, any electronic engineer, we probably class based on the semiconductor, electrochemical, piezoelectric sensor, and catalytic. For example, these sensor are using for the whatever or mobile automotive exhaust. For example, they use aluminum oxide and platinum wire as a sensor, and optical sensor, etc. In summary, I think one example I'm going to tell that I think this is a sensor people are using for the automobile. So these like inside it looks like, for example, they used a platinum AL203 sensor. So you can see the real, although a tiny sample, this is very useful for the oxygen sensing applications. Again, in summary, I think these are, suppose if you take any solid electrolyte, either garnet-based pellet and with silver paste, I can do this called a CO2 type of sensor, etc. In summary, I think if thin oxide is there, you can make a composite. You can prepare different type of sensor, N-type and P-type sensor, etc. So what are the other types depending on applications? I think depending on applications, people can prepare nano composite catalyst, either organic reactions, for example, different type of carbon. And then, so these are the, for example, nano composite, people can use it by the nanoparticle rod or for heterogeneous catalysis, depending on applications. What are the real challenges? Again, people want to be template approach, very complex molecules people can do, for example, silicate. And for example, people can use a copolymer approach, people can do, and fluorosurfactant, etc. Again, these are the specific applications people have been reported in the literature. In summary, I think some particular thing they want to be different type of structures is needed for the. Again, for example, for catalysis, I think material should be high surface area and pore size is very important. That's why they need a particular type of materials to prepare for the depending on the applications. So this is a summary. I think you can do the small lab with a different type of the applications we need. So regarding thin films are concerned, I think this is very important. So if you would work with the electronic industry, I think any electronic material, with the people, sometimes they use the chemical vapor deposition technique. It is nothing but reactant gases are introduced in the chamber. In a chemical reaction occurs on the wafer surface leading to the deposition of the substance. For example, there are different type of the things are available. For example, atmospheric pressure, chemical vapor deposition, and different, for example, CVD, low pressure, high pressure, or plasma CVD, etc., etc. Again, for example, you want to be dielectric applications. I think people can use this type of the CVD, and for example, silicon technology, people can use this type of to prepare the material. People can use. Another approach is the physical vapor deposition techniques. Here, no chemical reactions are not involved. Again, the vapor constituent materials are created inside the chamber either by condensation occurs in the wafer surface, leading to deposition of the solid films. Again, sputtering deposition, either you can do reactive, bias, or magnetron sputtering. Again, deposition methods, thin film, for example, especially here is the electronic application for IC circuits. I think they used atomic layer deposition or pulse layer deposition techniques, and epitaxy, CVD or vapor phase epitaxy, molecular beam epitaxy. These are all the very expensive techniques people can do. In fact, I know that the university, I think we are not able to afford this type of things. Again, the similar type of things we can do with the chemical methods. That's why, anyway, if you go for real, what they call as a device, large scale, I think these techniques are very useful. Again, in summary, depending on applications, optimization of thickness is needed. For example, magnetic property, they don't want too thick material, thin is needed, and composition and understanding the electronic and surface interface effects and mechanical properties. Very important if you are an electronic material engineer, you prepare any thin films or anything. I think these are the very, very important points you have taken into consideration. In summary, I think while playing the deposition rate, I think these are various important parameters. Thin film uniformity is very important, and deposition rate, and either you can deposit it either material, any metal or dielectric or a polymer you can do. And the quality of the film depending on the chemical and physical properties, electrical properties, mechanical. Already I mentioned that one, composition, stoichiometry, film density, and texture impurity, etc. And also in summary, again at the end, cost, depending on the application, if you do large scale, I think cost may not be a really big issue. So one example, if you take a sputtering, because this technique is very useful, if you play with power, total pressure, target substrate distance, and oxygen partial pressure, so you can play with the composition, morphology, and deposition rate. Either if you do electronic properties, again, I'm telling electrochemical is the battery. For example, you go for any electronic applications. That way, depending on application, you can play with this type of the things. So these are sputtering unit. For example, you can do different type of sputtering units are available attached to the glow box. Since your samples are hygroscopic, you have to use the sputtering unit for the attached to the glow box. I think it will be very useful. In summary, I think people can different substrate. I told you that the cathode, the target, and substrate. What will happen is during plasma ion is ionized to form argon ions and hitting. This is like billiard ball mechanism. When argon ions are hit into particular things, again go back to the particular argon he is going to deposit it on the substrate. Again, it's also very simple reality. In order to make 2 to 3, 4 elements, composition, reproducibility, a lot of things are there. So again, it is a research. For example, people want to be 2 to 3 different type of metal targets you want to deposit at a time. People can do the multi-target system. And I think 2 to 3 target, again, you can understand if you go for plasma engineering, I think especially all metallurgy and materials engineering, you're going to learn more in how to, especially depending on sputtering, different type of zones are possible. So is one example. I told the importance of Rutherford backscattering spectroscopy. It is nothing but it is a backscattered electron is hits on your substrate. For example, your carbon substrate sample. So backscatter electrons is the energy of the backscatter electrons means higher energy will come to the, for example, nickel has a higher atomic weight, it will come first, then lower, oxygen is light element. So this technique is very useful to know the composition and thickness and etc. homogeneity of the sample. And you can play with, for example, various sputtering parameters, etc., etc. And morphology. In summary, if you have the Auger spectroscopy, see the homogeneity. Your samples are all the elements are homogeneous or not. It will give the information. In summary, I think by understanding these techniques, very useful. For example, to know the composition, etc. For example, if you have silicon, so there again you use the RBS is a different approach. See the surface is what they call a surface defect, or is there any problem in the oxygen diffusion or not, they can study. So depending on applications, I think it uses RBS for the Rutherford backscattering spectroscopy as a technique to understand more depth, and people can do change the morphology, etc. Since already I talked about this, again the summary that so without sputtering, color will change depending on the, anyway, these are all things observation is needed while doing the sputtering of the material. So another technique is called chemical vapor deposition technique. I think this technique is very useful to understand, for example, any gaseous, for example, in here we need a precursor. For example, if the precursor should be volatile at low temperature, then the gas precursors will come to the reactor substrate. At a particular temperature, depending on that one, then particular oxides are going to deposit in the substrate. All the gases will come out. So advantage of, anyway, there is a lot of modification is happened because sometimes people are using the uh, heat or plasma, some depending on the rate people can do. Again, the story is that, for example, silicon nitride or silicon metals, they want to prepare. We need ammonia. If we want to prepare silicon nitride, we need nitrogen gas as source. Again, these are toxic, so to be careful because safety is also be taken to and gas absorption, so many things. And also these are the various types of the mechanisms is possible. This is one example. If you want to prepare any, for example, silicon metal, because the example silicon wafer. So these are the way people can prepare. Example, hydrogen gas is also needed. They use the silane, SiL, for this very corrosive toxic chemical. I think they use hydrogen as a gas because it's also, that's why depending on the reactor, I think the safety is a big issue we do with working with hydrogen. So that's why all they do work in industry. I think the safety also will take into consideration. Again, there are all the things, for example, large scale. I think, for example, any vapors or gases, I think they use the trap by using vacuum chamber, exhaust, all this one. They need to do with a proper control. Then only we're able to get since we know the corrosive gas, I think all this one take into consideration. So this is one example based on the, suppose you want to do any surface coating or anything, we can use this materials depending on the, again, high advantage is the like high growth rate possible and good reproducibility and hard, and also these are the advantages of this technique. In summary, disadvantages, for example, high temperature process and sometimes toxic and corrosive gases, especially if you come take into consideration about the chemical vapor deposition technique. I think these are the small steps. I'm telling that, for example, silicon, you want to get, these are the various steps. For example, silicon deposition, the 650 degree, the SiH4 will get silicon metal and reduction will occur. So for example, you want to prepare tungsten and nearly high temperature, or you want to prepare aluminum oxide. Yeah, these are the different type of the source, different way people can prepare the materials. For example, is very important. Another one is gallium arsenide. I think this is also one of the nice electronic material. So what they used is that gallium methyl, means trimethyl gallium is the source, and arsenide means ASH3 as a gas, and they're all the gas phase and mixed together. Finally, these are all things in to form a gallium arsenide solid. So remember, these are methane gas. That's why it's very toxic. That's why people have to dispose the gas in a proper way, and all quality controls take into consideration. And sometimes you work with the boron nitride. For example, this is also one of the well-known electronic materials you are going to use in your studies. Again, BF3 means trifluoroborane plus ammonia. Remember, ammonia is a nitrogen, so all this gas. Here, HF is a toxic gas, so that's why. So it would be, these are the various take into consideration. That's why sometimes while working with the electronic industry or process industry, also try to understand the safety of this. What is going to happening? Try to read the manual before doing anything. I think that is very important. Take care of your health is also will play an important role. So some of the other techniques are there, advanced, for example, nanolithography. So how much time I have, so that accordingly I'm going to talk. I'm going to finish up. Sorry.
We still have around 10 minutes.
Okay, no problem. Okay, so I covered a little bit. I'm okay. Thank you, sir. Thank you. I'll continue.
Okay.
So another one is advance of nanolithography application. Again, for example, metamaterials. I think people want to prepare lithography. For example, depending geometrical shapes and, for example, antenna. So they want different shapes. For example, IC circuits. Depending. So what they use is that they prepare substrate and a particular area they expose either a different type of the UV beam ray exposure particular beam, and they can get a, it is like a stamp particular particular area they can get, and finally they can fill and they can metallization, etc. People can do the they're all depending on the applications. Again, we broadly classified in UV lithography, I lithography, and G electron lithography, and X-ray lithography, I-beam lithography, etc., etc., and laser lithography. They're all the depending on the like what they call a technology, process technology. People can use different type of the things. Other technology, for example, nano imprint and UV crucible, micro nano contact printing, roll-to-roll imprint, and scanning probe techniques. Again, for example, micro nano contact printing, atomic lithography, soft lithography, etc. So these are summary. For example, specific photolithography can use it. For example, 2 to 3 micrometer thickness, and also for example, electron beam lithography less than 5 nanometer. For example, masks, IC production, and another way the focus ion beam nearly 20 nanometer, very low R&D. For example, plasmonic applications. And for example, nano imprint lithography, this is if you want to, minimum range is 66 to 40 nanometer. This is depending on bioelectronics and biosensors and nano channels, for example, nanowire, etc. And deep pen lithography also can use it for sensor applications, etc., etc. So what I'm telling that depending on the applications, people have different specific requirement accordingly. People can use. So nano imprint lithography, for example, the best way is that the first thing is that they use a substrate followed by mold, then heating the things, and particularly, and again rising followed by, depending on, again, depending on which is the things you want, and particularly people can prepare it is like, okay. So this is another way of technology. Another one is a UV curable technology. For example, what they will do is that they, for example, any batteries, some UV rays, when the polymers are there, particular mold, and then UV is going to be colored with UV irradiation. For example, photoionization will take part. Sometimes you take any monomers, particular things become polymeric. So at the time, it will be particular area only is going to cover that one, the polymer like that way. So these are various applications starting from nanofluidics, nanophotonics, biosensor, etc., nano devices, and optical component, etc., and silicon MOSFET in the electronic applications. So again, the charter challenges, nanofabrication, for example, templates in silicon, quartz, metals, plastic, and removal of residual resist, the de-shaping of the profile, and again, achieving the high accuracy also. Anyway, each technology it will be there, unless if you go more depth, I think we don't claim that one technology very useful for all applications. I think that's why there is a huge, what are the possible advancement of technology with engineering. I think people are adapted. That's why nowadays a lot of miniaturization, a lot every year. I think you buy any instrument every 10 to 5 to 10 years you have to change, because a lot of features are coming. I think that is the way we are progressing the advanced knowledge. Again, fabrication of the nano templates by using that high resolution electron beam spectroscopy, and then dye etching, etc. So again, the process exactly by using E-beam approach, and depending on the particular things, they can get nano contacts. And then, so again, the summary is that they want to fill with a different type of the layers. So they can use a different type of the, these are flow rate for the template, depending on the which template you want to use. People can use, for example, usually they use the polymer PMMA, polymethyl methacrylate is a polymer. So at the end with E-beam, because the polymer is easier to remove but a particular area, particular mode, I think there is a useful for this type of technology. Again, E-beam exposure. So this is a setup. In summary, for example, you want to prepare guns. E-beam resist is the things, the polymer consisting primarily in the monomer. So it is like I told you already, the irradiation of the electrons will lead to generic type of interaction with chemical bonds breaking the positive resist. So radiation induced in the polymer due to negative resist, and common negative, for example, people are using glycidyl methyl methacrylate copolymer. These are the polymer people are using for this type of the applications. Again, these are the performance and in proximity, etc. Since these are the advantages, again, geometry, only less than 1 micrometer can be generated, and vapors are patterned difficulty without any mask. This technique can be highly automated. I think electron beam is much greater depth than the optical lithography system. Disadvantage, I don't tell that. I mentioned already each technique has disadvantages. Disadvantage, electron beam lithography machine is very slow. Then approximately 5 substrate per hour at the less than 1 micrometer resolution. I think at the industry, they want to be not only slow, fast, because too slow also, it's not really economical. So application of the silicon chips, again, we remember people can use field emission devices and atomic force microscope. I told you that people, if you do electronic industry, people want to see atomic force microscope, they use a silicon tip, because again, is an electronic material. Silicon tip is a different type of, and also silicon tip can be used in the atomic force microscopy and biomedical studies. Again, the chips people can silicon tip effectively controlled by parameter like substrate time, etching time, flow rate, pressure, etc., and oxygen, nitrogen gas, etc. These are the different type of the chips, electronic, for example. So that's why a particular application where sharp tips is needed with silicon. So and also that's why these are all the electronic materials people can use it for the depending on the applications. So the process of the silicon, again, chips, I think people can, I told you already, you can do, if you want to be large scale, we have chemical vapor deposition in a particular area, we have to adopt the electron beam lithography approach. Again, people are using the UV, PMMA, and etching the surface. And finally, we can get a reactive etching. Again, this because particular application, they want to be particular type of shape. For example, T type of shapes, we need this type of technology. And for example, amorphous silicon carbide, I think particular applications are sometimes high aspect ratio. These are all like mold, so means particular mold, they can use it for depending on the applications. Again, UV curable nano imprint lithography, especially submicron phase grating, for example, is the meta material. Again, silicon template, can we use it for the, because sometimes depending on applications, they want to be width, everything should be very accurate. So these are the, again, the UV channel, UV curable nano imprint technology. So based on this scanning microprobe lithography, we can do probe like STM and AFM techniques. So since my time is going a little bit top, so I'm not able to discuss much on this the principle of this technique. So again, I told you already AFM. So usually, for example, dip and lithography. For example, people wants to see, for example, at a molecular level, what type of thing is going to happening with this type of material. So in summary, anyway, these are advantages. For example, resolution is dip and lithography resolution. They want to be 15 nanometer. I think we have to use this technique. Again, based on the AFM, especially ambient conditions, we can use ink theory, because people want to be, for example, again, people are using the ink as a organic molecules, people are biological molecules. So people, they can use various type of, for example, metals and metal oxide they can use. Anyway, depending on the application, for example, fluorescent dyes, they need a silicon oxide, or for example, metal salts for the electrochemical electrolysis deposition, and substrate, for example, gold and gallium arsenide and silicon oxide, etc. These are all the things. These are summary. I'm going to by ink theory. Okay. Again, advantage of the ink, for example, the same what they call inkjet printing. People want to use for the polymers. I think they're very easier. If you take with the metals or ceramic materials, a little bit complicated. Still, there is a lot of progress in this type of in this area. So again, current applications, DPN, especially especially for the biomedical manipulations and DNA, or for example, protein sequencing studies, I think detection. I think this, again, for the particular application, they want to be particular specific techniques are needed for the understand what is going to happen, especially, for example, sensing mechanism, etc. I think these are the obstacle. Again, the speed, matching ink substrate and current condition, a smooth surface, work on and learning how to write on. For example, write on. It's not like our printer, what you're using. I think each technique has a little bit advantage, disadvantages also there. I think due to time limitation, I think I prepared too much depth on characterization technique since already people know very well, and I'm not able to discuss too much since my time is too much. Like what is the time is going? So it took almost more than another 1 hour like that way. Still, that's why I think the conference chair has given nearly 2 hours. I think I have to finish nearly almost another 15 minutes. I have maybe 5 minutes. Simply, I'll skip this one. I don't need to discuss too much since at least you will give the flavor on what type of the characterization techniques and just for the images. I think all the people, it is not really new things. So for example, XRD, I think once you go to real setup, you can see some X-ray tube and the detector. And advantage of this technique is you can put the sample there and we can get a pattern. And okay, so for example, X-ray tube, there is inside there is X-ray tube. We can use either copper, cobalt, different type of source are there. And this is a principle of the X-ray tube looks like this way. Since I don't have time, just I'm going to quick slide within another 5 minutes. Okay, again, crystallography, we broadly classified into 7 space groups. I think that already people will know. And then crystals, since the time is moving up and various type of crystals are possible. Again, I think it will take more time. Again, sometimes people won't tell the crystalline and polymorphous things, etc. So again, the advantage of crystallography, we can know that what is if it's a perfect crystal or not, or the amorphous or nanocrystalline, you can tell. Again, these are one of the Bragg slide is very useful to understand the, again, any material, not only metallurgist, a lot of different type of applications. Again, since the time is going up, so I prepared a lot of slides since the time is moving up, so that anyway you can get a spectra and try to analyze based on the full width of maxima, if it is nano size or not, we can tell. And sometimes with this formula, we can calculate the crystallite size, etc. And then a lot of things are there and you can do. In fact, I think there are all things already I think we are going to taught by your professor, so I don't need to touch on this, on the details on this one. Since I have another 2 minutes, so I think you can do, for example, so important points and tell you that. So suppose you want to dope with any ceramic material, different thing composition, you can tell single phase or not, and sometimes you can do pattern matching by using software, etc., etc. Again, not only is, for example, you do X-ray is very useful depending on applications, for example, cement and biomedical, etc. And then thin films, and also we can use. And what are the possible software people can use is that Topaz or some Vista to see the crystal structure. And sometimes there are different type of softwares are available. Anyway, since Redwell refinement is all, I'm more specialized in Redwell. I don't have time to discuss too much on this one. In fact, future people can get the pattern analysis, all the things we can study. Okay, so my time is going up, I think. Anyway, since I'm telling that since you are the student, I don't want to go too fast the slides. So still this way, I would like to summarize since the time is. So I know that every student we have almost nearly 30 to 1 hour time. So if it is more time also is not much interesting for you people. So again, I think I'm going to, anyway, again, one example I want to tell you that I told you that if it is amorphous material, we don't see any, for example, the lines are very broad and we don't see any TM pattern. If it is nano size, we can see rings. If it is particle size increasing, we can see dot dot. This is a way you can get from the XRD information what you're getting with the TM. It's complementary technique. Again, what is the difference between SCM and TM? SCM is only scanning surface and TM is a transmitted beam. Okay, I think thank you very much. And then maybe these are all, again, I told you that these are various tips are using for the AFM. Again, either contact and modes is possible. I think I'm going to finish again TGA, DTA, etc. Okay, so I'm very sorry because I'm going to end. Okay, so and I think I'm going to stop by now. So maybe we can raise any question and answer. Is it okay?
Yes, it's all right.
Yeah, because another 10 minutes we can spend some question and answer that will be very useful. Okay.
Okay, thank you
So,
very much.
Yeah, most of the things I already your teacher would have told already, so that I no need to, since they are told the preparation characterization, I thought it made it more detailed study, so it is not so interesting. Okay, thank you very much, and then okay.
All right. Thank you very much for the nice lecture, Dr. Reddy. It's
Okay.
actually covering most of our lecture here for undergraduate students, and it's very comprehensive. So now I guess we will have time for Q&A session. So I
Yeah.
will give the opportunity for the students probably to ask the question to Dr. Reddy. Anyone who wish to give question, perhaps they can raise hands.
Sir, I can see any chart. I don't know nowadays.
It's just a notification so that they can.
Yeah. Okay.
Okay. Anyone from students, perhaps? No.
To our students, please don't be shy. Just ask any question to Dr. Reddy, the expert in
Yeah, okay.
materials. Yeah, maybe you can also ask how the experience Dr. Reddy start from the beginning as a very, good researcher. Yeah, how he studied Islam, something like that. Please, our student, you can ask any question to Dr. Reddy.
Yeah, you can
And you
ask.
don't have
Yeah.
you don't have much time. I mean, you don't have this opportunity so often.
Yes.
So
Yeah.
ask question. Please ask
Exactly,
question.
definitely what Dr. Redis has given this morning is really, really comprehensive. Then you can learn anything from him here. Please, yeah, ask question. Yeah, any question related will do.
And also I work with a lot of engineers, starting from metallurgist and then materials engineering, also biomedical, and some people background with the electronics, also telecommunication engineering also. I think those background telecommunication, then he did with masters MTech in nanotechnology, solar cell, so that's why sometimes it's really funny,
Your slide has given the proof, Dr. Reddy. Yeah, your slide has tell everything about that.
Yeah. So that's why I wanted to make them simpler. So sorry, I think principle of lithium battery, maybe I thought I explained next slide that I don't know, I risk too many details, especially how the lithium will move. I think you're able to follow. So hopefully, yeah.
No question from students. Perhaps comments from.
Yeah, I think we should give students a quiz then. Yeah.
Pop-up quiz, perhaps.
Yeah, pop quiz.
Okay, so now not a quiz. I think I wanted to suggest you all people. I think one way I think is a good institution, especially Indonesian university is one of the best metallurgical, and I thought one of the leading institution, and especially you people are specializing in the materials engineering. I think it's really good. Maybe for you a lot of good opportunities all over the world. That is the one thing I wanted to, including here, places like McGill, one of the English speaking university. Like other places you can explore is France, I think is Indonesia also. I noticed that based on my early experience when I was there in doing France, I met Irawan is my close friend. I think he's an Indonesian friend. He's really good and he helped me a lot. I think he's able to speak nice French also. That is the advantage you people in Indonesia. I think you can speak the good language. I think that is not a problem. And other places like for you is Japan is a good opportunity for you people. Okay. So these are the different opportunities, especially if you are materials engineers. Okay, and good luck. So always so don't be shy. And then I know that it is a little bit difficult. Sometimes the research with this age difficult to follow all the things. Still, the basic science, what you are getting from the information from your teachers, that will be very useful for you people.
Dr. Reddy, maybe I ask one question, one simple question.
Yeah.
How is the life difference between Singapore and Quebec, Canada?
Oh, so
In
entirely
terms
different.
of research life, yeah.
Yeah, research life is I cannot compare Singapore because see there I was a little bit. I have almost like everything I have to do, starting from I am a manager as a professor or like a lab technician. Everything I used to do there in Singapore. Here life is different, you know. Here here is a different case, you know. That's why I have more time, free time is there.
All
That's why
right, yeah.
yeah, nice to share my knowledge with some people. I think that way that makes me more, you know. Yeah.
Yeah, maybe next time we can arrange that. Perhaps for one specific topic, you can also give the
Yeah.
lecture,
That's
and
why
maybe we
in
can
fact,
arrange in year 2020. Next year, we still have more opportunity for that,
yeah, I
because
think
I
that will be
think,
better so that it will be slow and then some practicals it will make them is more
yeah.
so like 1 week course it will be better for
Right,
you.
right, yeah. That's maybe the, I mean, the schedule that we can arrange again next. Yeah, Dr. Saki, perhaps we can still, I mean, give Dr. Reddy slot for next year public lecture.
Right. Next semester we'll do, Prof.
Yeah,
Herman.
okay, exactly. Because Dr. Reddy, in his email offering, the course can be, divided into several talks. Yeah.
All right.
Yeah, in fact, why I'm telling that sometimes I know that is not so easy because sometimes I know each people have digestion up to 40 minutes, so sometimes too much also
Yeah.
not good also because anyway, still it will use the flavor because first time I'm giving the talk and also thank you, Professor Herman, and
Yeah, you're
also
welcome.
your
Very welcome.
department
Yeah.
and all colleagues. In fact, it's a nice opportunity. My personal experience, I'm telling that although Indonesia, when I was there, in fact, is good friends and we met them, and it's a good because a lot of people are more motivated, especially young students. I think
Yes.
you people have different. I don't care about language. I think that is not a problem. Overall, if people are motivated in science, I think that is very important. And okay,
Yeah.
what we, I think that way maybe you don't worry. So at least
Yeah.
that way is good, and keep going. That's all.
Our young generation here in Indonesia can speak English much more fluently at the moment. Yeah, Dr.
Yeah,
Reddy. So
I know,
yeah,
I know, I know.
why
It's not a
they don't
problem.
ask question, because maybe they are a bit shy. Yeah, but in terms of
Yeah, it's narrow. I
the
think one
fluency
question.
of English, they
Yeah.
can speak much better.
Yeah, there one question right here. Yeah.
Yeah,
Yeah,
please.
I wanted to maybe next time I'm planning to make if time possible, if time permits, I want to convert my slides to bottom some Google Indonesian. In fact, easier to say, like what they spell also Indonesian. I think I want to make if time possible. Okay. So one thing is that people have raised one question because they'd
Right.
ask you the circuit
Okay.
nano and because the circuit is different from small. Okay. So usually I don't know because maybe okay. People have asked about the circuit, electronic circuit. For example, it is a little bit different because if it is electronic in the electronic circuits, for example, resistor, capacitor circuit, depending on which type of the material. For example, if it's a supercapacitor, if you get one semicircle, means one resistor, one combination, one capacitor has to use. Suppose if you fabricate any electronic IC chip, for example, it contains silicon, there is a multi 2 to 3 layers are there. So what will happen is that a particular chip, you will get 2 to 3 response, you know. What you can tell, okay, this layer belongs to this one particular thing. And next one, due to response. So maybe I don't have much because board, what they call checklist and board to tell this one. Usually what the best way that if he's a really electronic engineer, so I wanted to stress too much on this one is that if you have a, based on the what they call intercept also, you can tell that your IC circuit is nice contact or not. That is the way the impedance spectroscopy it is very useful. Your resistance is what they call as y-axis touching the bottom and very sharp, clearly indicate that okay, oh, your circuit is really good or not, like, or sometimes it's a bad contact. Sometimes you may see that a lot of noise signal indicate, oh, something is wrong. That's why people will throw this circuit. They call it quality control. If you want to make a better, understand the quality control of any IC electronic circuits or electronic material, I think this is the way people can use. Okay, so that is my okay. Since I told you that it is very because since it is difficult, I think this is a way. Maybe I would have the checklist and board is there. I would have explained clearly based on the your okay your interest. So simple explanation is that one combination. Okay, I think this technique is very useful if you work with depending on the application. For example, ICs, supercapacitor, or ferroelectric material, or magnetic material, etc., etc.
Okay. Thank you very much for the nice answer, Dr. Reddy. So I guess that answer your question, Mr. Madioti.
Yes, it is my answer question of curiosity.
Okay, thank you very much. So is there any other question perhaps before we close this session?
Yeah, another 3 minutes I have. Okay, maybe.
Yeah.
So my suggestion is that because since although whenever I come to conference, I think people are like you, they are very shy. So my personal experience is around 2012. I came. My first conference was in Padijaran. At the time, people are very curious. I think at the end, after giving the talk, and then they realize that okay, sir, we would like to learn. And they came when I was in Singapore. I think they spent 1 week. And the idea is that curiosity, because in different way people will go, different way facility, there are access. I think still good that the Indonesian University, I think most of the things I have, based on my knowledge, I think you people are better than I think any Indonesian university. I think thanks for the reputation of all your department and the lecturers, and then you are the best. I think I can tell that you are the best people. Keep continue. That's all. Good luck.
Yeah, we are still struggling for, getting higher achievement. Yeah, Dr. Reddy. But
Yeah, it is great. In fact, I know no, my own personal experience. I'm telling that, because when I came to last 8 to 9 years, there is huge improvement, because now it is entirely different, especially all the students, they're able to present very well. I think language is not really barrier.
yeah,
Yeah.
Right. Thank you very much, Dr. Reddy. I
Okay.
guess that could thumbs up for today's session. So before we close this session, perhaps we can do a photo session together.
Yeah, please open the camera. Yeah,
Please, all the member to open your camera.
yeah, students, please on
Students,
your camera. Yeah, we can take the photo session together with Dr. Reddy.
Okay, so I will give you a few seconds to open your camera. Okay. I think for the first page is ready for photo session. 1, 2, 3, cheers. Okay, next page. Okay, thank you very much for all participants, especially for Dr. Reddy for this nice opportunity to give lecture to our students here in Metallurgical and Materials Engineering Universitas Indonesia. And perhaps, okay, here from Dr. Reddy, if you have any comments or question regarding this lecture, you can send email to in the chat box. Dr. Reddy already provide his email address and also his Facebook account. So you may contact Dr. Reddy through this email or Facebook. Okay, thank you very much, Dr. Reddy.
Dr. Reddy, thank you so much. Yeah.
Okay.
Thank you very much.
Yeah. Have a good
Okay,
sleep there.
thank you very much,
Because
sir,
already
Dr. Soyan, and then Harman. I think really after almost he's one of the young at the time. Really good. In fact, what I noticed is that the Indonesian you people, I think they're more mature. They're not like other PhD students. I think their way of working culture is different, and then in terms of maturity, what they call as that way is really great. And
and
I
we
think he's one of the top metallurgists. I think one of the
local minerals.
Ambon, really good. I think very, it really reminds me, I think really good,
Yeah, our
Thank you very
task
much,
here is to process our abundant local minerals to be processed further to be used as the electronic materials in the future. Yeah, that's actually our big duty for us here.
Yeah. In fact, I didn't discuss too much on that what they call recycling, because since my talk was, I think recycling also very big in the industry, because I didn't talk about too much. But metallurgist, I think we would concentrate on recycling. That is very important.
Exactly.
Pyrometallurgy, I think. So I thought it is like title is very. Didn't discuss too much. Still, it is. I'm telling it take a little bit more time. I think this is good. I think Herman, I think my suggestion is good. nice to concentrate that particular, especially recycling. Idea is that as a metallurgist, we have to educate the engineer. We don't care about all industry, like big profit. At least at the university level, we have to try and educate them. At least they go to industry, they feel for that. Otherwise, without proper training, I think they cannot do. That is my personal opinion. Since Indonesia, you have a lot of young students are there. I think they're able to do
Exactly.
well.
Okay. Again, thanks a lot, Dr. Reddy, for your very valuable time for us. Have a good sleep there because night in Canada, right? Yeah.
Yeah. No problem.
Yeah.
Anyway, it's okay. I think it's okay. 10 o'clock. Okay. Thank you very much. Okay.
Okay. See you and here,
Okay.
inshallah. Yeah. Okay. Bye-bye.
Okay, sir. Thank you very much, sir.
And
Thank
dear
you.
student, thank you very much for your kind participation in this guest lecture. Yeah.
Okay. Thank you very much. Anyway, good luck to all. Okay. Thank you very much. Bye-bye. Okay.
Yeah.
Okay, thank you very much.
I'm going to
Bye-bye.
Bye-bye. Yeah.
Yeah. Thank you. Bye.
you.